So, this is nothing but simply hysteretic and this is your FRL actually. So, you can see this is a, it requires 4 flip flops only to build a, and this is your digital accumulator and we are controlling here. So, one extra thing we have here. So, depending upon how many bits of accumulator you use, that will define the resolution of your frequency you can log to. So, let us say I am using 5 bit here, 5 bit means roughly 3% accuracy you can get. But if I want to log it at exact frequency, then you need to have some kind of analog control. With the digital, it is not possible. Until unless you have a 10 bit or so, then you can say, okay, I have a maybe 0.1% kind of accuracy. Okay, if you want a 1%, then 7 bit roughly. So, but the problem is more number of bits will complicate your R DAC. So, building a 8 bit or 10 bit kinds of DAC is not easy. Okay. It will take lot of area also, and guaranteeing that accuracy is also not easy unless you take care lot of things in the layout. So, what we are doing here, we are using a both coarse and fine. Coarse means digital, fine is some way of analog, and I will tell you what analog it is. So, we have split this resistor into two components. So, this is controlled by simple digital bits and this is controlled by, you can say this up down are nothing but PWM, and why it is PWM. So, what happens when there is a difference in the frequency between your reference and feedback clock. So, this is your feedback and this is your reference, then it based on the phase difference between the two, it generates up or down. Okay. With that, and up and down means one will be 0, other will be high, and the pulse width will be defined by the frequency difference. If it is a positive or negative, then you will get either pulse or up or down pulses, and the width will be defined by the difference between the phase, and phase difference is nothing but if you have a frequency difference, then there will be a phase difference. Okay. So, that is what you get. So, what would happen actually, if you look at this, if I have a, do you guys remember that we talked about this switched GM? Huh? We had a GM with a switch, and that PWM will control the GM of that. So, same thing can be applied to resistor also, correct. So, if I, let us say I have a resistor of value R, and if I give a, if I have a switch and turn on and off that resistor with a duty cycle particular at some frequency, then effective resistor will become D times of that R. Okay. So, the same concept is applied here, and so what would happen actually, now you can think about we have a two components in the RC time, one is the coarse, other is the fine, and this RP is component is coming from this. So, if you break your time constant in two components, when I say two components is tau coarse and tau fine, correct. So, instead of looking like this perfectly linear, so let us say, okay, so if you are looking, so if this is my clock, what I am looking at, this is my VC, and so it will charge like this, but nobody is asking me to, and this will be controlled by RC time constant. Okay. So, if I change the R, then the slope, entire slope will change during on time and during off time, but nobody is saying me like you keep the same slope throughout the all time. Like if this is T on, I can do this, okay, or I can do this also. So, which means the large fraction of that time constant I can control with fixed R, and a small portion I can control with some delta width. So, what I am doing here, so I have two resistors. So, if I call it, let us say Ri, Rp. So, this is digitally controlled and if I have a switch, let us say, so okay, let us take one. Let us take only this one. So, this is controlled by a, let us say, small. So, what would happen if I turn on? So, originally it will be Ri plus Rp, okay. So, if this is, let us say I call it T on and this is T off. By the way, this T on T off is not same as PWM, this is different. So, what will happen during T on? What is our total? Ri? Okay. And during T off? Ri plus Rp. So, which means your resistor is changed for that small. So, it's reduced. It's reduced means your slope will get faster. So, what if I want to increase? For delta amount I want to increase. So, you can do the same thing, and you can have another resistor. Let us say I call it Rp, and so you keep it on for most of the time and you open it for a small fraction, then what would happen? It will increase, correct. So, during off time you will still get Ri plus Rp, but if I open this for a very short time like this, then during this it will open and add it up. So, you will get Ri plus 2 Rp during that short period, and that is how you control the resistor. So, I know, and once you lock in the frequency with some phase difference, this pulse width will remain constant. If there is a frequency difference, then this every cycle this pulse width will keep changing. Okay. So, your course control is already frozen. Let us say now I am left with the 3% error, which is coming due to the finite resolution of that DAC I have. So, I want to correct that 3%. So, these up down and pulses will be generated based on whether it is a plus 3% or minus 3%, and that will control this. So, depending upon up or down coming, you have to control one of these two resistors, and it will change the resistor value, okay, or you can say it will lock with the pulse width for which the two frequencies are same, and since this time is constant for this PWM, so they will exactly lock at the same frequency. So, I am not using any analog or anything here, it's everything is done digitally, and this high resolution path or fine control is done using only PWM like control. So, you do not need any like a very I mean complicated analog to do this actually. So, it is as good as analog without using any analog component, you can say, in this particular control. So, that is what we did in this, and this is what happening. So, this is permanently on. So, when down comes, it will open it and add the resistor. When up comes, it will close it and reduce the resistor, correct. So, this will work like a fine control, and once it is locked, this pulse width will keep coming. So, you can say these two frequencies will lock in frequency, I mean two clocks will lock in frequency, but not in phase. I mean they will, when I say lock in the phase, their edges will not be aligned, they will be slightly shifted because of this fine control, because you require that to correct for that extra error which is coming from your this deck or course control. So, and this is what I was talking about, this current sensor is nothing but your RC, and you can see this is I mean if you look, I mean this is a power FET, and we know power FET will in any case will be much large, but if you look at this, this is the largest component here in the control. The reason is because those R value, I mean value of R is order of mega ohms and C is tens of picofarad. So, this is what, so this is with the without fine control, only coarse, and you can see your frequency is not locked at a, I mean there is no single tone as such. Its reason because I am using only 5 bit. The moment I turn on that fine path, you can see I mean this single tone. So, it locks exactly at the same 1 megahertz frequency, and you can see with the output voltage profile. Remember the duty cycle curve. So, when the output voltage is changing, it is as good as changing the duty cycle if it is V in fixed, and we know it will be parabolic, and that is what you are seeing the this variation in the frequency, and with that FLL you get a constant frequency 1 megahertz. This is your transient response 0 to 600 milliamp 1.2 volt. So, 28 into roughly 56 to 60 millivolt undershoot usage, okay, which is 5% of this 1.2 volt, and I am using 1.8 micro and 10 microfarad. I mean 1.8 micro is slightly on higher side comparing 10 picofarad cap. Usually try to keep 10x kind of a separation between these two. So, if I use a 20 microfarad, obviously it will improve, or I use 1 microhenry and 10 microfarad, then you might see better response. So, what happens, but now you have a, so if I do try to do this fixed frequency hysteretic converter, what is the drawback of this? Can anybody tell? Do you see any issue by adding this FLL loop?
Like while changing the R DAC, the switching will also introduce some transient.
Not really actually. It's this is accumulator, so it will not change very fast.
So that RP switching will also introduce some.
No, that it doesn't actually. Because in the steady state, it will not do anything. Once it is locked, it's locked. I mean, during transient, in any case, output changes. So, during transient, only these guys will respond. When you have but if it's a slow change, then they will slowly take over, and that will not get effect will not be seen in the output. So, one thing you have to remember, this FLL has to be very slow. The reason is, if I make it very fast, what would happen? You are going towards a normal PWM control, and what was the advantage of hysteretic? Fast transient, because your comparator can respond very quickly, and the transient improvement is achieved only because it is a non-synchronous. So, comparator can turn on and off all the way, okay, which means during transient frequency is not defined here, okay. It could be anything, it could be turn on all the way for 2 or 3 clock cycles, you do not know. And that, but if I force a particular switching frequency, then you are again going towards that synchronous version of that, I mean the reason we are getting it's a non-synchronous. Now you are trying to again synchronize by locking to a particular clock frequency. So if this guy becomes dominant, I mean comparator is saying no, I have a transient, I want to on for entire period, or I want to basically reset or set the duty cycle immediately, but this guy will say no, now frequency is changing, okay, I will not allow to do this because you are changing the frequency now. So you cannot make this path very fast. If I make it fast, then within 1 or 2 cycle it will try to correct, which will hamper your transient response. So better make it very slow. So during transient I will allow the comparator to take over and correct the transient, and over the time slowly I will allow this guy to correct the frequency. Only then you get the benefit, otherwise all the benefits will be gone off what you achieve with the hysteretic. So this is very important actually. So the frequency correction loop should not be very fast, otherwise it will degrade your transient response. So in this case, if you see here, during this transient for maybe I think 5 to 6 cycles, the frequency is not same as your steady state frequency. So transient comes and your duty cycle is changed, and if you look at a period here, it will be different than this actually, it is not same. Okay. And here I made the proportional path, which is your up controlled by up and down, the fine path little bit stronger, otherwise you could have seen this guy maybe on for a longer period actually. Okay, so this is taking still 2 to 3, so it is not like exactly looking like a hysteretic. If you remember, in the hysteretic we had completely on for a very long time until your inductor reaches, but it is taking few cycles. Okay. So another advantage is like is stable for different values. So so this is actual measured result on the silicon. Instead of 1.8, I put a 4.7 micro, which is more than 2x. It's like 2.5x of the inductor. If you do this with the voltage mode, I mean you have phase margin, everything defined at one particular LC. It's possible that it may become unstable. Here is still stable, and you can see the transient response also doesn't look that bad, because look at the capacitor value, I am not changing 4.7 micro and 10 microfarad. I mean this is a very bad choice actually, I would say. You never want your cap to be too small for such a high inductor value. Okay, I would like to keep maybe 10 times of that 50 microfarad. So, but still it is I'm trying to show, I mean even if you choose the, I mean you make a bad decision in taking this inductor and capacitor values, still it's stable actually, it's not that bad. Okay. So there is one more benefit of this hysteretic. You guys remember the PFM mode? How did we do that? We had the same thing, hysteretic comparator. Okay, and you look at the output when it discharges below your this lower threshold, then again comparator trips and charges the output. So you automatically get the PFM here. You don't require two different controls here. So when you go in the light load condition, all you need to do, just do a zero cross detect, that's it, and turn off this switch, or the frequency will be automatically taken care by comparator. One thing you have to remember, I don't want frequency to be locked in PFM, so you have to disable this FLL in PFM, that's it. Otherwise it will try to force the same frequency and you will never go in PFM mode. Okay, so when the moment you enter PFM mode, you disable this FLL and the PFM loop will take over, and the same comparator, everything else will remain same, they can be used as it is. So the control is simpler here, no compensation is required. The PFM mode is also simpler because we are using same comparator in both the cases. So the only drawback will be maybe you need to check, accuracy may not be as good as, so it's a non-linear, there is no integration is here happening. So accuracy, but still you get a decent accuracy. Even if you want accuracy as good as we already talked about, you can use integrator in the feedback and adjust your VREF So, in the steady state you can still achieve the similar accuracy by adding an integrator, which is not difficult.